Welcome to Module 7 on kinetics of rigid bodies under planar motions. This module also goes by some other names such as Newton-Euler equations for rigid bodies under planar motion, or planar kinetics of rigid bodies using Newton-Euler equations and so on. But ultimately we are talking about relating the forces and the moments with the acceleration. So in the previous module 6 we have seen that if you have a rigid body, okay, and you know, let's say, the velocity and acceleration of a point, okay, so velocity could be in one direction, acceleration could be in another direction. This is point A, and we knew the angular velocity as well as angular acceleration of this rigid body. Then we could find the velocity of any other point on this rigid body as well as acceleration. And the two fundamental relationships that we used were that velocity of B, choosing A as a reference point, was this, plus omega cross R of B with respect to A. So that was the vector. And acceleration of B was acceleration of A minus omega squared R of B with respect to A plus alpha cross R of B with respect to A. So these two relationships were obtained for translating frame. If you use a rotating frame where there is sliding happening on a rotating rigid body, then you would have to use expanded equations, which we wrote for rotating frames, okay? But the basic idea was that you were doing kinematic analysis of rigid bodies moving in a plane. So as you can see in these two equations, we know the velocity of one reference point, we know the angular velocity, and knowing the geometry, we can compute the velocity of another point, and we can do something similar for acceleration. We need to know omega, we need to know alpha, we need to know acceleration of a reference point, and that gives acceleration of another point, right? So when we talk about velocity and acceleration analysis in Module 6, we really didn't talk about what gave rise to those motions, okay? But there were forces and the moments applied on the rigid body that gave rise to these accelerations. So there could be a force applied this way, another force applied that way, maybe even another moment applied about center of mass, okay, something like this. And all of these forces and the moments that were applied on the rigid bodies gave rise to the acceleration, okay? Now for this particular module, the center of mass of the rigid body would become a very important point, okay? We will often talk about the velocity and acceleration of the center of mass. And in fact, one of the things that we would often do in this module is try to determine the acceleration of the center of mass as much as possible, as well as the angular acceleration of the rigid body. So when I give you a general method to solve the problem for kinetics of rigid bodies under planar motion, then one of the goals would be to find the acceleration of center of mass as much as possible, as well as find the acceleration, angular acceleration. And if you can't find both of them independently, at least find a relationship between the two. So in this particular module, now we will begin to relate the forces and the moments applied on a rigid body with the kinematic performance of the rigid body, which is typically reflected in the acceleration of center of mass as well as angular acceleration. So you can think of this module analogous to module 3, which was about kinetics of particles. So kinetics of particles related the forces applied on a particle with the acceleration that resulted from it, right? And that was done using sigma f equal to ma. So we will definitely use relationships like Newton's second law, and we will see how they apply for a rigid body, which truly speaking cannot be seen as a system of particles. It's actually a continuous medium, okay? But you will see we have similar relationships for rigid bodies moving in a plane as well. So it is this particular module where some of the greater benefits of learning dynamics would be truly realized. Many of you would recall in my one of my introductory videos that I showed you guys some very simple homegrown robots, and I talked about we have certain kinematic performance we're looking for from the robot, and we want to know what kind of torque should be applied at the center of the wheel, what kind of friction forces should be present so that the robot does not slip. So those are the kinds of questions that we will be answering in this particular module. Just as we had relationships for the kinetics of particles, we also have kinetics relationship for rigid bodies moving in a plane and even for space. So let's just do a quick recap for the particles, right? For the particles, we had seen that if you have a particle and there are forces applied on it, then sum of the forces is equal to the mass times acceleration, and that was our Newton's second law, which could be only applied in an inertial or Newtonian reference frame, right? So that's what we had for one individual particle. We could also extend it for a system of particles. So system of particles, you had a system of particles, multiple particles inside the system, and let's say one particle pi, there were external forces applied, so you had Fi, and then you had Fij, and Fij is small Fij represented the internal forces. Then for the system also, you could write a similar relationship, which was that sigma F equal to mass of particle I times acceleration of particle I, and the internal forces occurred pairwise. They were equal in magnitude but opposite in direction, so they cancel out. So when you wrote this Newton's second law for individual particle and you added it together, you only had external forces on the left hand side, right? And we also saw that this could be written as the total mass times the acceleration of center of mass, right? So this is the center of mass, then sigma Fi was also equal to m times Ag. Now it turns out that even though we derived this relationship for a system of particles and a rigid body is not a system of particles, you still derive the same relationship. So I'm not going to go into the derivation for that, but this particular relationship still applies even for a rigid body. So if you are given a rigid body, and if you know its total mass and you know the acceleration of center of mass, then the multiplication of the two, the product of the two, is equal to the sum total of all the external forces acting on a rigid body. Okay, so this also applies for rigid body. And Euler is credited for actually deriving these relationships for a system of particles as well as rigid body. Newton's second law actually is only for a singular particle, but when you extend it to a system of particles as well as rigid body, which is seen as a continuous medium, then we say that Euler is actually the one who created these rules, and that's why this particular governing principle is also called Newton-Euler equation. So Newton-Euler equation, okay, and it's also known as Newton-Euler's first law. All right, so first law. Let me write that. So the Newton's second law for a single particle was written as sigma equal to ma, but was also written as m times dv over dt, which was nothing but d over dt of the linear momentum, right? So we had this Newton's second law reformulated as sum of the forces equal to rate of change of linear momentum, right? And then we also saw that we could relate the angular momentum with the sum of the moment applied on a particle. So if you had a single particle P, moving with some velocity, let's say Vp, and you picked a reference point Q, not necessarily a fixed point, then we saw that sum of the moment applied on the particle P with respect to Q was equal to rate of change of angular momentum about Q plus velocity of the point Q cross m times velocity of P, right? And that allowed us to relate the moment of the forces acting on P with respect to the point Q with the rate of change of angular momentum. So if Q was a fixed point, then this term would be 0, or if VQ and VP were parallel to each other, then also the second term in this equation would be 0. And for a system of particles, we obtained a similar relationship. So for a system of particles, with multiple particles in here, with a let's say reference point being G, center of mass, we obtained that sigma mq of the system, so we had again a reference frame and a point Q, was equal to h dot q, so h dot q of the system plus, and then the last term changed slightly from VQ cross MVP to MVT v of G. So velocity of center of mass, right? This is something we derived in the module 5, right? Now the question is, do we have something similar for a rigid body as well? And it turns out that this exact relationship is valid for a rigid body as well. Just as it is valid for a system of particles, it's valid for a rigid body as well. Which means that if you have a rigid body and let's say the velocity of the center of mass, whatever it might be, and you pick a reference point whose velocity also may be known to you, then you can take the moment of all the forces acting on this rigid body about point Q, and that will form your left hand side. And on the right hand side, if you can write h dot q of the system, then you'll be able to relate the sum of the moment with the rate of change of angular momentum of a rigid body, right? So at this point, before we proceed any further, having opted in the Newton-Euler equation, the Newton-Euler first law, let's see what HQ of the rigid body looks like. Okay, so I'm going to write the angular momentum of a system of particles. So this is revisiting it. And again, whatever I'm doing for a system of particles actually is applicable for rigid body as well. Although the exact derivation is slightly different. Instead of saying individual particles, you will have a differential mass element dm, and then that's how you would actually compute all the terms. So we have a system of particles. Let's say this is particle pi, and we have a center of mass, and we have a lot of particles around here. We have O as our reference frame, and then we have a point Q. Okay. So HQ of the rigid body, or the system, let me say, is equal to sigma r of position vector of I with respect to Q cross mi velocity of the particle I, right? So that's the I over here. And then, of course, center of mass may be also moving, so that has velocity g. And r of I, which is Q, is basically this vector. Okay, so that's the position vector of I with respect to Q. Notice this is not a position vector of particle I with respect to the origin of the reference frame, right? We can pick any arbitrary point about which we want to compute angular momentum. So just as you can compute moment of forces about any point, you can also compute angular momentum of a system or a rigid body about any chosen reference point, right? So at this point, I'm going to introduce a couple of new vectors over here. So one vector I'm going to call this vector, the position vector of center of mass with respect to Q as rho, okay? And I will call the position vector from G to Pi as rho I. Okay, so rho and rho I are, relative position vectors, right? So rho is the position vector of G with respect to Q. So let me write that. So rho is equal to position vector of G with respect to Q, and rho I is position vector of I with respect to G. Okay, so R of I with respect to Q can be written as rho plus rho I, right? So it is this vector. So from this triangle, this vector is equal to rho plus rho I, right? And that's fine. All right. Now Vi itself, which is the velocity of the particle I, can also be written as, so velocity of particle I can be written as velocity of center of mass plus the velocity of particle I with respect to G, right? And that is velocity of G plus rho I dot, right? So that's nothing but the derivative of the position vector of I with respect to G, okay? So what I'm going to do is I'm going to substitute these two relationships, 1 and 2, into this over here. Okay, so H of Q of the system is equal to sigma rho plus rho I cross mi times Vg plus rho I dot, right? So we substituted both of those in there. And now what I'm going to do is I'm going to expand this. Okay, so this is equal to sigma. Now rho is not dependent on any of these indices I. So what I can do is I can write this as sigma rho cross mi Vg. Let me just finish writing this first, and then I'll simplify it. Plus sigma rho cross mi rho I dot plus sigma rho I cross mi Vg, and the last one is plus sigma rho I cross mi rho I dot. Okay, so I have not introduced any simplification so far. I just did the cross product. Okay, now we'll look at the simplification. So clearly rho and Vg are not dependent on the I, so I can easily write this as rho cross sigma mi, which is nothing but the total mass, times Vg. So sigma mi, let me write this over here. Sigma mi is written as the total mass. Okay, so we get rho cross mg over here. Sigma is gone, of course, because we did sigma mi, plus this would be rho cross sigma mi rho I dot, plus this would be sigma mi rho I, and I can take Vg outside, so that becomes cross Vg, and the last term is plus sigma rho I cross mi rho I dot. And now I'm going to just leave it like that. Okay, let's look at second term over here, rho cross sigma mi rho I dot. So first of all, what is sigma mi rho I dot? Right, that's what we want to know. What is sigma mi rho I dot? All right, and I'm going to tell you that this is actually equal to 0, and the reason for that is very, very simple. What this is computing is the relative velocity of the center of mass with respect to itself. Relative velocity of the center of mass with respect to itself, of course, has to be 0, right? And if you can see that, over here, then you just have to go back to the definition of the center of mass. Definition of the center of mass is mrg equal to sigma mi, not rho I actually, but ri, right? So that's the definition. So how is this obtained? You look at the position vector of these particles with respect to the center of the frame, and you multiply them with their masses, you add them together, and then you finally divide by m, right? And Ri can be written as sigma mi rg plus rho I, right? Now what is rg over here? Rg is actually this position vector. This is rg plus rho I, right? So that's something we can definitely write. So what do we get here? So this becomes m times rg, because sigma mi is m, plus sigma mi rho I, and on the left hand side we have mrg. These two cancel, so we get sigma mi rho I equal to 0, and that makes sense. Why is this quantity 0? This quantity is 0 because this is computing the center of mass of a system of particles with respect to itself, and the center of mass of the system of particles with respect to itself, of course, has to be 0. And if you differentiate it once, you get sigma mi rho I dot equal to 0. And if you differentiate it even once more, you still get the same result. That's also 0, right? These are all 0 quantity. So which means that sigma mi rho I dot is 0. And that means that this term drops out. Sigma mi rho I we have also seen is 0, right? So we have only two non-zero terms left here. So let's write them again. So HQ of the system is equal to rho cross mvg plus sigma rho I cross mi rho I dot. So this is sigma rho I cross mi rho I dot. Okay, let me just write this again. This is rho I dot. Okay, right, this is rho I. Alright, so there's not much simplification we can really achieve with this term, so let's focus on this one. What is this mi rho I dot, right? So rho I dot is the relative velocity of the particle pi with respect to center of mass, right? Because this is what rho I is, right? Now from the previous module on kinematics of rigid bodies, we know how to relate the velocity of the 2 points, right? So if you look at the point pi and we look at the velocity of the center of mass, we know there is a definite relationship between the two. And what is that? That is velocity of the eye is equal to choosing g as a reference point, this plus omega cross rho I, right? This is how we relate the velocity of the 2 points in a translating frame, right? Assuming we are using a translating frame. And vi minus vg is nothing but this relative velocity of rho dot I, which we are interested in, right? And that is equal to omega cross rho I. So we can make this substitution in here, right? We can make that substitution. So what do we get? So this is HQ of the system is rho cross mvg plus sigma rho I cross mi omega cross rho I, right? So let's focus on this term now. Okay, so this is basically A cross B cross C. So from the cross product of three vectors, what is this quantity? This is A dot C times B minus A dot B times C, right? So you know how to take the cross product of three vectors. So that means we'll do rho I dot rho I, and that will give us rho I squared. So this becomes sigma mi rho I squared omega minus A dot B. So that's rho I dot omega. Now, if a rigid body is moving in a plane, which is what we are focusing on in this module, then we know omega is perpendicular to the plane, rho I is in the plane. That means rho I dot omega would be 0. So we will have only this term left. So this is equal to rho cross mvg, right? Now, for a system of particles, this tells you how the mass is distributed around center of mass, right? But if you were to do this analysis for a rigid body, in fact, instead of this term, you will get integral dm rho squared, right? For a rigid body, instead of a particle, you will pick an infinitesimal mass of, let's say, mass dm, right? And this is your center of mass, and this is your position vector rho. Then integral dm rho squared, as you will recognize from your statics class, is defined as nothing but centroidal mass moment of inertia. Right? So this is the moment of inertia about an axis that goes through the center of mass, and it tells you basically how mass is distributed around the center of mass, right? So for some of the common figures like a ring, where most of its mass is concentrated at the periphery of radius r and m, Ig is given as m times r square. If for the same mass, same radius, you have a disk or a cylinder of radius r and mass m, Ig is given as mr squared over 2. For a sphere, it is 2 over 5 mr squared. For a bar of length L, mass m, it's ml squared over 12, and so on, right? So for some of the common shapes, I will expect you to remember what the centroidal mass moment of inertia is. At the same time, I expect you to remember, how do you obtain mass moment of inertia about another axis that is parallel to the axis going through the center of mass using parallel axis theorem. Okay, so some of the basic stuff that you learned here in your statics class, you should remember. And if you don't, I would advise that you look up that chapter from your statics book and refresh your memories. Okay, all right. So this quantity over here for a rigid body would be Ig omega, right? So we get rho cross mvg plus Ig omega, and that is your HQ for either a system of particles. So I'm going to drop writing system now, because this is valid for a rigid body as well. So angular momentum of a rigid body is now given by rho, where rho is the position vector of the center of mass with respect to your chosen point Q, cross m times Vg, which is the momentum of the center of mass, also the momentum of the rigid body, plus Ig omega, right? Okay, now let's take the derivative of this angular momentum. That's when the fun stuff will happen. So h dot q is equal to, I'm going to write Ig omega first, and of course the inertia is not going to be changing over time, so Ig is a constant, and derivative of omega is nothing but the angular acceleration, so that's alpha, plus derivative of rho. So rho is the position vector of center of mass with respect to q, so that's actually going to be Vg minus Vq, because that's rho dot g, cross mvg plus rho cross m times acceleration of center of mass, right? Okay, so what else do we get? So we have Ig alpha plus Vg cross mvg will be 0, so this actually is minus Vq cross mvg plus rho cross m times acceleration of center of mass, right? And on the left hand side we have h dot q. So I'm going to take this and bring it on the left hand side, and I get h dot q plus vq cross mvg, which is basically nothing but the sum of the moment about point q, as we have seen before. So if you go back over here, right here we have that equation. So sigma mq is equal to h dot q plus vq cross mvg, And remember, everything that we have done for a system of particles also applies for rigid bodies, okay? And I'm not giving you proof of that because the derivation proceeds along similar lines, except that it involves, integration and things like that, okay? So this is equal to sigma mq. So this quantity is equal to sigma mq. That's the moment of the forces about point q. And on the right hand side, we have Ig alpha plus rho cross mag. So let me write this again because this is an important equation. Sigma mq is equal to Ig alpha, and instead of rho now, I'm going to write R of g with respect to q cross m times Ag. And this equation is called Newton-Euler equation number 2. So this is what we call second law of Newton-Euler. All right. Now we add the word Newton with Euler because Newton proposed these equations for a particle, and Euler extended them to a system of particles as well as rigid bodies. So now the comprehensive name is Newton-Euler equations. Okay. If you look at this particular equation, again we can get some special cases because we want to see how we can simplify our life, right? So for example, if let's say the acceleration of center of mass is 0, then the second term would drop out. If you pick the g to be the same point as q, which will happen quite a bit. So if q is equal to g, which means that your reference point is actually the center of mass, okay? So you're taking the moment about center of mass, there's no separate point q, then also this term would drop out, right? Because r of g with respect to q would be 0, so r of g is q would be 0, and in that case, sigma m g is equal to Ig alpha, okay? So what this is saying is that if you know the angular acceleration of a rigid body, and if you know its centroidal mass moment of inertia, then if you take the product of the two quantities, that would be equal to sum of the moment of all the forces about center of mass. And that's it. So as far as this particular chapter is concerned, the only two equations you will need are sigma F equal to m times acceleration of center of mass, and sigma m g is equal to Ig alpha. That's it. These are the only two equations you need, and these combined are called Newton-Euler equations. So you see, in terms of remembering the formulas and expression, there is not much to remember here, right? Significant ma is something you already know for a particle, and it applies for a rigid body also now. The only difference is that for a rigid body, different points on the rigid body can have different acceleration. So when we apply this law, we say acceleration would be acceleration of center of mass. And at the same time, because the rigid body is not a particle, it could be rotating. So it will have non-zero angular acceleration. So if you know the non-zero angular acceleration, you know the centroidal mass moment of inertia, you can relate it to the sum of the moment of all the forces acting on a rigid body. So it is sufficient to remember just these two equations, and you can solve pretty much every problem in this module. And I'm going to give you a general method for solving the problems that would proceed along similar lines as we had done in Module 3 on kinetics of particles. You can solve pretty much any problem in this chapter. But you would remember that in your statics class, sometimes you took moments about points which were not necessarily center of mass. And you did that because, it made your life a little bit simpler to take moment about a point through which most of the forces were passing, and you were not interested in computing those forces, so it made your life simpler. Similarly, over here, sometimes you may want to take moment about a point that is not necessarily center of mass. If that's the case, then this is the equation that you should be using. So if you pick any point that's other than center of mass, then this is the equation that you should be using. Okay, so you will notice that if you take moment about another arbitrary point q, then you have this extra term over here, unless something special happens and which makes this term to drop out.